Hi, welcome to part two of this talk on combination theorems from geometrically finite convergence groups. So just a reminder, this is based on a paper which is joint work with Alec Traaseth. Um, so the basic question that I want to address in this part of the talk is starts with the following setup. I have two geometrically finite convergence groups which act on the same space Z. So both of these groups are subgroups of the homeomorphism group of the same space. So examples that I mentioned on the previous talk, you can think of G1 and G2 as being discrete subgroups of PON1 or PUN1 and the induced action by homeomorphisms on the ideal boundary of either HNR or the action on HNC. Another context that I won't talk about as much here is if G1 and G2 are quasi-convex subgroups of a relatively hyperbolic group H. In this case, the convergence group action comes from the action of this group H on its Bowditch boundary. Okay. And the basic question, like I said, is we want to know when is the subgroup of the homeomorphism group of Z generated by G1 and G2? Let's just say, when is this geometrically finite? In the first example, this is just, when did these two discrete subgroups generate another geometrically finite discrete group? And for the second question, this actually, you can rephrase this as asking, when is the subgroup generated by G1 and G2? When is this subgroup G1 and G2 and H, when is this also quasi-convex? Okay, so the theorem, which is joint with Alec and myself, says that you can answer this question by basically by playing ping pong in the boundary action. Oops, this should be Z, not M. So once again, I have the setup. I have two discrete convergence groups acting on the same space Z. I'm going to let G denote the subgroup generated by these discrete convergence groups G1 and G2. And I'm going to let J be the intersection of G1 and G2, which may or may not be the trivial group. I have to assume, this is an assumption, that this group G is actually acting as a convergence group on Z, but this is going to happen automatically in both of the examples that I mentioned on the previous slide. Okay, so what does the theorem actually say? So there's a little bit more setup. We have to say, suppose there exists a pair of J invariant sets B1 and B2 inside of my space Z, which both have non-empty disjoint interior. And these sets have to satisfy the following properties. First, the limit set of each of my groups GI is almost contained in these sets BI. In fact, the limit set of GI minus the limit set of J is contained in the interior of the set with the other index. It's contained in the interior of B3 minus I. So G1 is contained in the limit set of G1 is contained in the interior B2 and vice versa. And also these sets have to satisfy the property that for all G in Gi minus J, if I hit the set Bi, if I hit the closure of the set Bi with G, then it gets sent into the interior of B3 minus I. Okay, So the conclusion of the theorem then is that if you can find this pair of sets which have this ping-pongy type behavior, first of all, you can conclude, first of all, there's an isomorphism between this group G generated by G1 and G2 and the abstract amalgamated free product of G1 and G2 over the subgroup J. And also, these groups G1 and G2 are geometrically finite if and only if the group they generate is geometrically finite. Okay, before saying anything more about this theorem, let me try and illustrate what's going on with the examples so you can try and understand exactly what this ping pong setup is telling you. Okay, so here I have a subgroup of PSL2R, which is geometrically finite. In fact, it's convex co-compact. This is a free group sitting inside of PSL2R. It's generated by two elements, G1 and G2. And the action of this free group on the hyperbolic plane, it's not co-compact. It's going to be, the quotient is a surface with this big infinite flaring end. So these green curves are translates of the geodesic corresponding to the commutator of G1 and G2. So the subgroup J in this case is going to be the group generated by the commutator. It's the commutator subgroup of G1 and G2. And in fact, what happens here is that the limit set of this group is going to be contained. The limit set is always contained. Let's just put this in black. So the limit set of this group, which I'm going to call G1, is contained in the union of these four intervals in the boundary. And so the convex hull of the limit set, the convex core, is contained in this region right here. It has more than four boundary components. It actually has infinitely many corresponding to all of the different translates of J. So what you can do is you can actually just, in fact, not only, more generally, the limit set is not just contained in the limit set, it's not just contained in these four intervals. I mean, it's contained in this interval here, which we can call, let's call it B2. And what we can do is we can actually take a conjugate of this group G1 and arrange it so that the interval B2 is instead sent to this interval B1 with the same endpoints. And now the point is that any element of G1 which is not actually in the commutator subgroup will take the commutator subgroup to one of these other green geodesics. So in fact, any element of G1 which is not in J will take B1 to a closed subset of the interior of B2. And yeah, if I take this conjugate of the same group I'll get the exact same picture. Any elements in this conjugate subgroup, in this conjugated subgroup, whose limit set will lie in the closure of B1, will take the closure of B2 into the interior of B1, and then the result is they'll get an amalgamated free product of two surface groups along a closed curve, or sorry, an amalgamated free product of two free groups along a closed curve, and the result is a geometrically finite, in fact, co-compact surface group acting on H2. So this is hopefully a familiar picture. This is just to illustrate like exactly the kind of ping pong that this theorem is supposed to use. I should mention also that there's a version of this theorem for HNN extensions. I think there is no additional insight to be gained in saying exactly what that version of the theorem says. It is the same philosophy, but there's only one group. You're just gluing it to itself. You're gluing a subgroup of that group to itself via some element. Okay. So I should also mention so this theorem is really telling you how you can glue together, or rather how you can build new geometrically finite subgroups, say of isometry groups of rank one symmetric spaces, or more generally negatively curved Riemannian manifolds. You can find new ones by sticking two ones that you already know about together if they're configured in exactly the right way. So theorems like this have been around for a long time. In fact, theorems like this have been around since the days of Klein. There's a version of this theorem that's in fact due to Klein himself. But the other important things to mention is that when G1 and G2 are actually Kleinian groups, then the theorem on the previous slide, and in fact some more general versions of it, were proved by Maskett back in the 70s and 80s. And more recently, the same theorems proved by Maskett were actually proved for any discrete subgroups of PON1 by Liu, Shika, and Wang. So really, this theorem on the previous slide, the new cases that it's telling you about are really the cases where, for instance, G1 and G2 are subgroups of PUN1 acting on complex hyperbolic space. And also, this is giving you a new theorem when G1 and G2 are what's called fully quasi-convex subgroups in some relatively hyperbolic group H. And, in principle, this could apply more generally, but these are, I think, the two most interesting cases where you might want to apply the theorem. Okay, so how does the proof go? So I'm mostly going to talk about this implication where if you have two geometrically finite groups, you know that the group they generate is geometrically finite. The theorem does go the other way, but this is sort of the more interesting and useful application. And I think to illustrate the proof, I'm going to start in a special case where the intersection of these two groups is actually this subgroup J is actually trivial. So in this case, things are quite a bit simpler, but you can still illustrate the way that the proof goes. So let me start by illustrating my sets B1 and B2. So the limit set of G2 is contained in B1, and the limit set of G1 is contained in B2. In this case, where this subgroup J is trivial, you actually get to assume that the closures of B1 and B2 are disjoint. They don't intersect at all. So the main idea is to try and use the characterization of geometrical finiteness that I mentioned at the end of the last talk. We're going to use this, but in terms of characterizing the topological dynamics of the group action on its limit set. So we need to prove that every point in the limit set of my new group is either a conical limit point or a bounded parabolic point. So let's think about what can happen. So first of all, if a point X in the limit set of G1, in the limit set of G, it's possible that this point could be equal to some point to GZ for some G in my larger group G and some Z in the limit set of one of my subgroups. And maybe it's possible that this point X is actually a translate not just of any point, but it's a translate of a conical limit point in one of these original limit sets. It's not actually too hard to show directly from the definitions that in this case, the point X, which is a translate of Z, is actually also conical. This is just a very straightforward application of the convergence group action conditions. You have a convergence, this sequence realizing the fact that it's a conical limit point, just basically given to you right away. Okay, so points like this, we're fine. If we look like translates of conical limit points, then we're fine. Actually, the same is true if you happen to know that the point in your original limit set is parabolic. it is pretty easy to see that in this case, then in this case, any translate of it also has to be a parabolic point. There's a little bit more work to do in that case. And then it's even a little bit harder, but still not too bad, is showing that if you start with a bounded parabolic in one of your original limit sets, then in fact, any translate of this point is still a bounded parabolic point. This step is a little harder. There's some actual non-trivial work to do in this case because bounded parabolic points, the condition is that is asking for a co-compact action on the limit set minus the point. The stabilizer of the point acts co-compactly on the limit set minus the point. And in my original group, this meant that I had a co-compact action on, say, lambda of G1 minus some point in G1. And now I'm asking for a co-compact action on a much bigger limit set, the limit set of lambda of G minus the same point. And the stabilizer is actually the same size. The stabilizer will end up being no bigger in G than it is in GI in this case. So you need to do something to prove that you actually have a co-compact action on this much bigger limit set minus a point. But I'm not going to say too much about how that works. It actually uses some ideas that I'm going to bring up in a second. So the main step here is to try and understand what happens to the other limit points in G that are not just translates of limit points of one of my original subgroups. So in other words, what happens if X is in lambda of G, but where I delete all of the translates of my original limit sets. Okay, this set is not empty in general. So what are we going to do? We're going to use ping pong to see that X is actually conical. Okay, so what's the picture here? So I'm going to take my point X. It turns out that any point in the limit set of G has to lie in the union of these two sets B1 and B2. So I can say X actually has to lie, maybe it lies in this set B1. Okay, so I know X, it's in the limit set of G by definition. So I can usually write it. That means essentially I can write it as the accumulation of some orbit. Really, I can think about this as happening as the accumulation of some orbit given by some sequence gamma k in G. And this isn't quite true. This is a slight simplification, but I can basically think about this group element gamma k. I can always write it in this kind of alternating form, where it looks where I first take an element of, say, G1, and then an element of G2, and then an element, I can write it as this kind of alternating product between elements of G1 and G2. This actually uses the fact that this ping pong setup already tells me that the group G is isomorphic to a free product of G1 and G2. This doesn't use convergence dynamics at all. This is just the ping pong lemma that tells me that I have something isomorphic to a free product. So when this happens, well, because I have this kind of ping pong description of my element gamma k written as an alternating product of elements of G1 and G2, I get a nested sequence of sets. When I apply this element gamma k to the set B1, first gamma k maps B1 over into B2, and then, first HK maps B1 over into B2, and then GK maps it back, and then HK minus 1 maps it back, and then so forth. So the upshot is that I get this kind of nested sequence of sets bouncing back and forth. And this is also not obvious, but you can prove that this nested sequence of sets that you get from ping pong must intersect exactly in the point X, whenever X is a limit of a sequence that looks like this. So now I just consider the sequence gamma k inverse, which is just the formal inverse of my previous sequence. H1 inverse G1 inverse. And now what happens? Well, let me draw it. So if I apply gamma k inverse to the picture that I had before, okay, so I still have sets B1 and B2. They're the same that I had before. The point x, well, if I make sure that I take a sequence of even length, the point gamma k inverse of x will end up in B1. And I can also think about what happens to this sequence when I start applying it to B2. Well, if you think about it for a sec, because I have this alternating sequence of elements of G1 and G2, the ping pong goes backwards, and I actually get a nice nested sequence of sets like this. So somewhere nested in here is gamma k inverse B2. And maybe you can convince yourself by staring at this picture that what actually has to be happening is that gamma k is one of these sequences realizing the fact that x is a conical limit point, because gamma k inverse x up to subsequence is converging somewhere in here in B1, and gamma k inverse B2, this big set with non-empty interior, actually is converging to basically a point. You have to prove that this happens, but you can. It's converging basically to a point inside of B2. So I have this big subset, which is converging to a point, and that point is actually going to end up being far away from gamma k inverse x. So this realizes the kind of separation that I have to see that I have a conical limit point. And this is basically the proof. There are details to check, but once you've checked them, you've shown that this point is a conical limit point, and then you've proved that every point in the boundary, every point in the limit set of G is actually a conical limit point or a bounded parabolic point, and thus G is geometrically finite. So that's how the proof goes in the simple case where J is the trivial group. So we can think a little bit about what goes wrong if J happens to be non-trivial, and we have to deal with some amalgamation. So in this case, it's a very similar picture, but our sets B1 and B2, they must intersect, in fact. If J is infinite, then B1 and B2, the intersection of their closures contains the limit set of J, which will be non-empty. So we can try and do the same thing. We can take a point X, like we had before, and think about having this kind of nested sequence of sets decreasing down to X. Yeah, we have this kind of nested sequence of sets decreasing down to X. It is, again, you have to actually prove that this sequence of sets exists for an arbitrary limit point in the original group, but this is doable. It's essentially a combinatorial argument. And now you want to try and find this kind of sequence realizing the fact that X is a conical limit point. So you build it the same way that you did before. It's going to look like an alternating sequence of elements in G1 and G2. And now, when you apply that sequence of elements to your picture, okay, if we take something of even length, then we can ensure that gamma k inverse x still ends up inside of B1, but possibly gamma k inverse of x ends up really close to the boundary of B1. And if I apply the sequence of inverses to the set B2, then once again, I maybe get like some kind of nested sequence of sets. But it is actually possible, this nested sequence of sets in the picture on the bottom here, they don't actually have to be, it's not a, for each k, I get a different nested sequence of sets of length k, so they're not always nested inside of the first set that I look at. So it's possible, and in fact this can happen if you're not careful, that the sets gamma k inverse of B2, these could accumulate on the intersection between B1, the closures of B1 and B2. And this would cause a problem. I would not be able to see that X is a conical limit point using the sequence gamma K. because I need to actually make sure that gamma k inverse of x is converging far away from where everything else is converging. I'm supposed to see that these points look like kind of the opposite endpoints of a geodesic. And if they're converging to the same point, then they don't really look like that. So the trick here, in this case, is I can fix this problem by applying an element of J of the intersection. And I really have to use the fact that in my assumptions, J was a geometrically finite subgroup. Because what I'm going to do is I'm going to apply an element of J to this whole picture. And okay, when I do, maybe after I do that, this point, let's call this JK gamma k inverse of x. Maybe that still ends up close to the intersection between my two closed sets B1 and B2. But if I pick my element, J of J carefully enough, I can actually ensure that this nested sequence of sets coming from applying this whole sequence to the set B2, I can actually ensure that JK gamma k inverse B2 is far away from the limit set of J. In fact, so as a consequence, it's going to be far away from, this is not immediate, but it turns out that means it's going to be far away from the intersection of my two original sets, B1 and B2. So it's actually sort of not obvious. It's not at all obvious that such an element of J exists, that you can use an element of J to kind of push this nested sequence of sets away from the limit set. You have to do some work to prove that this can be done. And the key idea here for constructing this element this element of J, we actually have to use the fact that the group GI is relatively hyperbolic. And the fact that J is geometrically finite means that this is actually a quasi-convex subgroup. In fact, it's a little bit stronger. J is what's called a fully quasi-convex subgroup in the group GI. So why is this important? The important thing here is that we're going to actually end up using the coarse metric geometry of the group GI. So basically, I want to emphasize in the setup to this theorem, there was no, at least immediate assumption that the group GI had to be a relatively hyperbolic group. It turns out this actually follows from the assumption that we're starting with geometrically finite convergence groups. Those turn out to be always relatively hyperbolic, which means that you actually can say quite a lot about the metric structure of the group itself. And then you can use the metric structure of this group itself to try and understand how to find elements of J that sort of push you away from the limit set. This relatively hyperbolic structure, it comes directly from the convergence action, which means for the entire proof, you don't need to use any geometry in some like space that's given to you, whose boundary is actually Z. So we do need to use some metric geometry, some coarse metric geometry associated to the groups G1 and G2, but the space that they're acting on by convergence groups, we never need to care about the intrinsic geometry of this space at all, which is very nice because it leads to kind of proofs that strip away any kind of unnecessary details. And it also leads to some, maybe I'll just hint at, possible higher rank generalizations. So everything that's I've been talking about so far has been about geometrically finite groups acting on spaces with negative curvature. If you wanted to try and think about combination groups for combination theorems for groups acting on, say, higher rank symmetric spaces, essentially these same techniques should work. Things will be a little bit more technical and a little more complicated, but the point is that for like generalizations of geometrical finiteness in higher rank, a lot of the topological dynamics that make this theorem run, they actually do basically hold. Just, you need there's a few more technical assumptions that you need to impose because they don't hold in a quite as nice way. Okay, I think that's all I want to say. Thanks for watching.